Welcome to this Global Derivatives webinar, the very first of our new webinar series. I'm Antoine Savine. I am a quant at Danske Bank and a professor of finance at the Copenhagen University. We will also be live tweeting this webinar, so you can join in the conversation using the hashtag #GDWebinar. Computational efficiency is the #1 focus for quantitative finance professionals, such as myself. Complex transactions and, more importantly, regulatory calculations require time-consuming algorithms such as heavy Monte Carlo simulations, and to produce accurate values and risk sensitivities in decent time is a major challenge. To address it, quants like myself are working day and night to produce more efficient algorithms and also code that utilizes hardware more effectively. My company, Danske Bank, has been particularly active in this field, and we even won the Risk Award for in-house system of the year 2015 for our work on fast calculation of CVA. Therefore, it is my pleasure to host this webinar today and welcome Robert Jeva, the head of the Financial Services Engineering Group at Intel, who will demonstrate how we can use advanced programming techniques to utilize modern CPUs to their full potential and achieve impressive speedups. More specifically, Robert will lead us through different forms of CPU parallelization, which combined may speed up some financial calculations by up to 200 times on a Xeon server without any additional hardware. Now, before I hand off to Robert, I'd like to remind you that we will be holding an interactive Q&A after the presentation. If you have any questions during the presentation, you can send them to us using the orange Ask a Question button at the bottom of the screen. And now, over to Robert.
Thank you very much. By way of introduction, I'm a senior principal engineer at Intel. My background is in compilers. I've been working on various compiler projects for over 20 years now, some of them in code generation and optimization, and most recently in language extensions for parallel, vector, and heterogeneous computing. Then I chose to make a slight change, and rather than build products, I prefer to work more with customers and help them use our products and deploy them. So now my team is focusing on collaboration and joint project with customers in the financial services industry, where we collaborate to improve the performance of their financial applications, such as Monte Carlo simulations and PD solvers, by way of parallelizing and vectorizing their code. The current fall is a chart, and it's showing the performance of the binomial options algorithm. The y-axis is billions of options per second, which means higher is better. The x-axis is the 7 recent Xeon server products from Intel, denoted by the year of introduction rather than by their commercial name. So from 2007 till a few weeks ago, where we introduced the most recent codename Broadwell Xeon server. All of these are measured on the dual socket configuration, and the 4 lines are 4 different ways of running the algorithm, where the bottom blue line is single-threaded and scalar. The orange line is also single-threaded, but now it's vectorized. The gray line is not vectorized, and it is multi-threaded. And the yellow line is multi-threaded and vectorized. The yellow line is where my team and I would like to see all our customer code. At every point on every one of the servers, when you parallelize, you get a lot of performance improvement. But the amount of improvement is growing up interestingly over time. You get much more improvement in the recent Xeon servers than you got in earlier Xeon servers. The source code is always the same source code. We recompile it in order to take advantage of the new vector technology. So on the older server, we had the SSC technology, then we had AVX, then we moved to AVX2. Those do require recompilation, but none of these require rewriting of the source code. And now I'm showing 4 additional algorithms just so that you don't get worried about something being anecdotal about the one I was focusing on. Many other algorithms have the same behavior of they gain performance when you parallelize them, and they gain a lot more performance on the more recent servers. If you had an impression of what a CPU is, dating back for some time ago, and you evaluated, is it worthwhile, is it cost effective to parallelize my source code on a CPU, and you have done it a few years ago, this data is showing that you likely saw that it doesn't win you much, and because parallel programming is very hard, is very error-prone, it's very time-consuming, it's very costly, you might have had the conclusion that it's not cost-effective, that it's a lot of work for little return. The new servers change that equation. The new servers say that for the same amount of investment, the same amount of complexity of parallel programming, the return on investment in terms of performance is completely different, is much higher, and that changes the equation of the total cost of ownership. So just to illustrate, right, this is a die photo of one of the recent CPUs, and it shows with highlight of these yellow rectangles that I added on top of the die photo how it is that it has very many cores, which of course, as you saw, changes over product generation. That was a die photo of a single socket, and I'm showing here too, just to make it simple, that with a dual socket you simply get twice as many cores. The cores are obviously one and the most obvious hardware support for parallel computing, but not the only one. Within a server, you have that number of cores. In addition, inside every core, you have the single instruction multiple data technology, which we normally abbreviate into SIMD, which allows you to operate on multiple data items in one single instruction. In the illustration here, you see the 256-bit wide vector, which is what is being available in the AVX and AVX2 technologies, and it's divided into 8 lanes for the case in which the operations are single precision operation. Then you have what we sometimes refer to as vector lane. In every lane, you do an operation on one data item, and then you have multiple data items in your vector register, so you have multiple lanes. The way it works is that the width of the register is fixed, so the number of data items you can fit into a register depends on the size of the data type. You can fit 8 single precision, also you can fit 8 integer values into a vector register, but only half as many double precision values, only 4 double precision value in the same register. So it would mean that when you work on double precision values, the number of vector lane go down from 8 to 4. So the number of vector lane is not hard-coded in the hardware, the size of the register is, and the vector lanes is more of a mental model that we use to think about how the execution proceeds of the single instruction multiple data operations. So, to further illustrate the point, software that corresponds to what I was showing before in the blue lines, which correspond to single-threaded, non-vectorized applications, they use very little of the CPU hardware resources. Everything that I paint here in black is being unused with that kind of software. Most of the CPU is being unused, instead of using all the CPU resources that are available within the Xeon server that many people have. To do the math of the growth of these vector lanes over the product generation, I have this very simple metric which simply counts the number of vector lanes in a server. The server of 2007 had 4 cores in a socket, so 8 cores in a dual socket server. The SIMD widths of SSE as well as SSE2 and SSE3 and SSE4, all of them are 128 bits, which means if you look at single precision calculation, you divide it by 32 and you get 4 lanes in a core, and then all I done here is I multiplied that by the number of cores, and it ends up to be 32 vector lanes in the server, in the whole server. You do that for every server in the 7 servers that I've used to measure. The core count is growing from 4 core to 6 core, meaning 12 cores in the dual socket server, all the way up to 22, which is what we have launched last month in the end of March. In the end of March. We launched Broadwell with 22 cores per socket. These are physical cores. These are not hyperthreads, but in a dual socket it goes up to 44. And with 256-bit wide register, you get 8 vector lanes. And so all you do is you do the multiplication, and then I plot them in a chart, and you see how significantly this line is going upward. You can say that this is one manifestation of Moore's law, of how hardware resources are increasing over the product generation. Of course, if you plot over this product generation the frequency, you'll get more or less a flat line. The frequency is not going up, not because of lack of transistors, but because of the power limitations. So instead of raising the frequency, which due to the power limitation we cannot do, we raise the hardware resources dedicated for parallel computing, and this is a very simple metric. It does not necessarily reflect all the support for parallel computing, but it's a very simple metric, shows you that the hardware resources over time grow quite significantly. And you remember the yellow lines from a few pages ago. You can remember that some of them have very similar shape to the shape of the hardware resources. The way we accomplish this in software is by parallelizing the algorithm. This cannot be accomplished by the hardware alone. We have no technology in which you deploy age-old hardware that was not parallelized and the hardware can make sense of it, or for that matter a compiler or any automatic tool can make sense of it. The challenge now is on quants like Antoine and others, and on us at Intel, and many others for that matter, to develop the right parallel algorithms, languages, and techniques. So there's a whole stack sitting on top of the hardware that we have to use well in order to extract that level of performance from the hardware. Roughly, I would divide those into 4 considerations. One is make good use of the cores that you have, which can be deploy an instance of the problem on every core. And as long as that scales with the memory that you have, that is the simplest way of taking advantage of the cores. We know that it doesn't always scale, and so the other way of taking advantage of the core, which is more scalable, is via multi-threading. Intel has a few solutions for that. Of course, others have other solutions for that as well. We have OpenMP, TBB. In the financial services industry, TBB is more preferable to OpenMP. OpenMP is more preferable elsewhere. We have vector programming, which is the way you take advantage of the SIMD technology. We find that this is the least understood of these aspects, and where my team brings more value to our customers within those joint projects I've been mentioning before. Parallel programming means that the parallel algorithms have to be memory efficient and cache efficient. Having many threads missing the cache is way worse than having few threads missing the cache, and so cache efficiency is critical, as well as data layout. The data layout has to be different, and the alignment has to be different than the intuitive way you would do that if you were not to parallelize your software. So the way it would look is, this is a simple illustration of a Monte Carlo, and all this is the baseline sequential implementation of it. And the top line now showing up in yellow is the OpenMP way of multi-threading it, and this technology is available since '97. This is the first thing that was added to OpenMP 1.0, the idea that you can write a loop in C and on top of it put a pragma saying this loop is parallel. One thing that Intel was able to influence into OpenMP 4.0 is a very similar syntax, but now it says here's a loop and it's a vector loop. It has a very similar look and feel to the parallel loop in OpenMP, but it really is a single-threaded loop that the programmer said the loop has to execute in vectors, which is powerful because it allows us to get rid of the compiler's ability, more so inability, to prove that a loop is vectorizable. So we relieve the compiler from that responsibility, give it to the hand of the programmer. Now the programmer said this loop is a vector loop. What the compiler needs to do now is generate vector code for the vector loop. And of course you can do both, which is what we have done in the cases of the yellow lines. And you see that parallelization or multi-threading and vectorization are independent of each other. You can do either one of them. You don't have to do them in the same loop. You can find an outer loop where you would parallelize and an inner loop where you would vectorize. You don't have to parallelize and vectorize the same loop, or you can, depends on what works best in your case. And they have some consistency between them, and they fit nicely within the OpenMP framework. The concept I mentioned of parallelizing an outer loop and vectorizing an inner loop is our #1 best practice. This works well for CPU parallelization. The simple rationale is that parallelization incurs a runtime overhead. There's always some library that has to account for the multi-threading and affinitize the work to a core. There's some overhead associated with that. And in order to amortize that overhead, you want a big chunk of work, which typically you find in an outer loop or in some coarse granularity of computation. Vectorization has no runtime overhead, so the need for large pieces of code goes away. Instead, you want the lanes, because they execute in lockstep, you want to keep them nice, coherent, not too much control flow divergence, not too much memory access divergence, and therefore you want to your best chances to find those are in innermost loops. This is TBB on one page. For those who are less familiar with TBB, it is a C++ library, compiler independent. It is available in open source. You can study it very closely. And the heart of it is the task scheduler. The task scheduler is based on dynamic work stealing, which has the side effect of load balancing. It's a very nice property, which means that your application can be complex, combined together with libraries, combined together with components developed by different programmers or different teams. And when you integrate all of this together, no single programmer has to understand the overall parallelization and be able to load balance it by design. Load balancing happens dynamically as a simple side effect of the fact that scheduling is done via work stealing. It's a big advantage, and we have been able to leverage it in a few projects. Vector programming, as I mentioned, is now part of the OpenMP standard. Roughly, it has two parts to it. One is the one that I showed, illustrated on the top box, saying that the loop is a vector loop. And the second part, illustrated in the bottom box, is the ability to say that a function is a vector function. Intuitively, what a vector function means is that it is being compiled as if it was a body of a vector loop. This allows you to write modular code. You don't have to write all the code that you want to execute in vectors inside one big loop. You can break it up into modules, into functions, declare those functions as vector functions, and know that you are not going to lose performance in the interface. Solutions for data layout. We have a library that allows you to declare your data through the library, write object-oriented code, and the library interface will lay out the data for you such that all the red fields are consecutive, which is efficient for vector access. I want to mention our StackA2 benchmark. StackA2 is somewhat known and popular in the financial services industry. It is specified by the customers and implemented by the vendors. We had an implementation a few years ago where the time to calculate the Greeks took us just below 6 seconds, and we used OpenMP for parallelization. In the second trial, we moved from OpenMP to TBB, which improved our parallelization dramatically. So good sound parallelization is as important as good hardware, and in this case it mattered a lot. And as we moved from one generation of Xeon to the next, we also moved from 5.8 seconds to 1 second. We kept improving both on the hardware and on the parallelization technique. While we keep using TBB, as you can see, we actually improved the algorithm and removed bottleneck and improved the scalability from one release to the next. And the best we got, as you can see in the one result before the last, is 0.216, which represents a 27-fold improvement from our initial result. And with that, we only have 5 more minutes of time. I'll open it up. I'll give it back to Antoine and see what questions we might have time to answer.
Thanks for that presentation, Robert. Very, very interesting stuff. If you haven't already done so, I encourage you to submit your questions via the orange Ask a Question box at the bottom of the screen. Robert, your syntax, the syntax that you showed for vectorization in OpenMP is new. Are we going to see similar syntax in other C++ compilers and perhaps even in other languages?
Thank you for the question. Very good question. In fact, yes to both. The syntax that I showed obviously is being supported in the Intel compilers, and we in fact supported it even before it became part of the OpenMP standard. There is work going on to implement the syntax in the open source compilers, namely GCC and LLVM. And we are working with the C++ Standards Committee to introduce a syntax that will have much more of a C++ look and feel. So rather than having the pragma syntax, it will have the C++ look and feel of taking an API, a library style API like a for each, and take a lambda and vectorize that. We are also working on vector variants of some of the standard template library algorithms such as std : transform. So you'll be able to write a transform, give it the same iterators you give it today, give it the same function object or lambda that you give it today, but you will have a syntax to specify that the transform has to execute with vector policy, and then we'll have a vector implementation of that.
Thank you. How do you advise to deal with control flow in vectorized code, given the requirement that the exact same instruction must be applied at the exact same time, but to different numbers?
Right. So it's a matter of your algorithmic constraints. You will get the best speed up if you don't have control flow divergence in the SIMD algorithm. Sometimes it's unavoidable, and the compiler actually has no big problems vectorizing code with if statements and control flow divergence inside them. You can even have a loop inside the vector loop where the number of iterations vary between different vector lanes, and through application of masking, that all works well, and the speed up that you get will not be optimal. So when you have no control flow divergence, you are a lot more likely to get linear speed up from vectorization. When you do have control flow divergence, you are a lot less likely to get linear speed up. You'll get as much speed up as your algorithm allows, and in some cases that will be the best that you can do.
Thank you. You indicated that the core count on CPUs is growing up to a few tens, but then GPUs have thousands of cores. Doesn't it mean that they are better suited for parallelism?
So not necessarily. They require a much larger fan out from the software in order to keep their hardware busy. But the overall performance is a multiplication of how many resources you have and the performance you have in every one of those execution units. So a GPU is going to have more of them, but at 1 gigahertz, and the performance of every one of them is very low. The CPU is going to have fewer of them, but very high performance of each of them. So the multiplication can fall anywhere depending on your workload. And what we are seeing is that if you average the comparison across enough workloads, you end up on balance. They're equivalent. You get up equivalent performance between a CPU and a GPU. None of them is a huge winner.
Thank you very much. That's all we have time for, I'm afraid. Thanks for joining us today, Robert. We're really excited about seeing you again at Global Derivatives in just a few weeks on 9 to 13th May. If you have any feedback on today's webinar or any recommendations for future webinars, please do complete our short survey at the end of this webinar. It should flash up on your screen shortly. Thanks and goodbye.